In section 2.5, we're going to look at limits as x goes to negative or positive infinity. So these would be limits at infinity. Before we do that, I would like to look at the limit of a fraction of the form a over x, where a is just a non-zero number. And we'll look at what happens when the denominator, x, goes to either negative or positive infinity. If you want to think about that, it's a fraction where the numerator stays the same, but the denominator keeps going. So the fraction as a whole is going to approach 0. So for example, if I had 1 over 10, and I kept increasing the denominator, 1 over 100, 1 over 1,000, and so on, what's going to happen is, as the denominator grows, the whole fraction is getting smaller and smaller, or getting closer to 0. So this is going to be a very important concept when evaluating limits in this section. So let's look at what limits as x goes to negative or positive infinity means graphically. So if we look at this graph, I'll just call this graph F. And from algebra, maybe you could see that we have a horizontal asymptote of y equal to 1. Okay? So this is just a horizontal line, and in our case it's y equal to 1. The ends of our graph are going to approach. We don't really care what's going on in the middle of the graph, just at the ends. So we can describe these horizontal asymptotes using limits. So if we take the limit as x goes to positive infinity of our function f, notice that as the x values get larger and larger and larger, our y values, the graph, is approaching y is equal to 1. And if we look at the limit as x approaches negative infinity of our function f of x, it does the same thing. As the x's approach negative infinity, the graph here is approaching a y value of 1. So if you take the limit as x goes to either negative or positive infinity, and you get a real number, then that would be our horizontal asymptote. And I'll use HA for horizontal asymptote. So in this case, we have a horizontal asymptote of y equal to 1. So something to note is that we never write the horizontal asymptote as just a number. Remember, it's the equation of a horizontal line. So in the box below, this describes horizontal asymptotes using limits. If you have numbers L and M, and you take the limit as x goes to infinity, and it's equal to some number, L, then that would be your horizontal asymptote. So remember, I'm just using HA as an abbreviation. If you take the limit as x goes to negative infinity, and that's equal to a number, then y is equal to the number m would also be a horizontal asymptote. Remember that horizontal asymptotes are describing the end behavior of a graph, and there's only 2 ends to a graph, so we can have, at most, 2 horizontal asymptotes. It's possible to not have any, or to just have 1, but at most 2. So in this second graph, and again, these are going to go on forever. I'll call this G. Notice that if we take the limit as x goes to positive infinity of G, it's going to be positive infinity. So as the x's get larger and larger and larger, so do our y values. They just keep increasing. And if we take the limit as x goes to negative infinity of our function g, it's going to be negative infinity. So again, as the x values get smaller and smaller and smaller, moving towards negative infinity, our graph keeps getting smaller and smaller as well, also approaching negative infinity. So in this particular example, there is no horizontal asymptote. So in order to have a horizontal asymptote, the limit has to approach a number, no horizontal asymptote, if the limit goes to negative or positive infinity. And that's what we have in this box below. This is just notation. If f of x becomes large as x becomes large, then we write the limit as x goes to infinity of f is equal to infinity. And then we have similar notation if the limit is negative infinity, and if x is approaching negative infinity, going to infinity or negative infinity. So in my notes, this is supposed to be 241. So you can ignore the 205, the non-zero number. So let's look at some special types of functions. We're going to look at polynomials, and then we're going to look at rational functions. So remember, polynomials, they're just a big string of terms. They're written in descending order, where n is the largest exponent, and n is also going to be the degree of the polynomial. So there's some properties to this theorem 2.6 when you're looking at polynomials. The first is, if n is even, then when we look at the limit as x goes to negative or positive infinity, it will always be equal to positive infinity. So for example, if we have x squared plus x minus 1. Okay. Now x to the n is the leading term, so we're kind of ignoring the x and the 1. So as we go to negative or positive infinity, this will be equal to positive infinity. So 2, if n is odd, then as we go to positive infinity, it's positive infinity, negative infinity is negative infinity. Property 3 is what we were talking about earlier with fractions. If the variable is in the denominator of the fraction, then the limit's going to be 0. And the fourth property just has to do with the limit of a polynomial in general. As you go to negative or positive infinity, the limit will be positive infinity or negative infinity. And this depends on the degree of the polynomial and the leading coefficient. So the leading coefficient is the a sub n, and that will determine whether it's a negative or positive infinity. Let's go ahead and evaluate a few limits. In this first one, all I'm going to do is plug in infinity so you can see what it looks like. So this is going to be 1 over infinity plus 5 is just infinity minus 100. So remember, if you have a fraction where the denominator just keeps growing and growing and growing, that's going to go to 0, which means this limit is just negative 100. So we're supposed to identify any horizontal asymptotes. Well, since the limit is a number, then our horizontal asymptote is going to be y equal to negative 100. Okay. In this second example, we're taking the limit as x goes to negative infinity. Now, I don't like that negative in the front. So if you choose, you can just go ahead and factor the negative out, or you can just go ahead and plug this in as the negative infinity to the 6th power plus negative infinity squared, which would turn into a positive infinity, negative infinity plus 7. So I kind of wanted to see what this looked like. Notice that I'm going to have a negative infinity plus infinity plus infinity plus 7. And I have a problem with this because this is indeterminate. Whenever you have positive infinity minus infinity, so it'd be like a minus infinity plus infinity, we don't know what that is. Okay, so it's this form here. So notice if I exchange the first two terms, I have infinity minus infinity. And that we don't know what that is. It's not 0 because these terms are growing at a different rate. So we have to be careful with that. What we're going to do is a technique that we often use in calculus. We create fractions if we get an indeterminate form. So the way that I'm going to create a fraction is I'm going to factor out the highest exponent, the x with the highest exponent. And in fact, I'm probably going to go ahead and also take out that negative because it really kind of bothers me. To write the negative limit as x goes to negative infinity of x to the 6 minus x squared plus x minus 7. So that's going to be equal to negative, and here I'm going to create my fraction by factoring out x to the 6. So that's going to leave 1 minus 1 over x to the 4th plus 1 over x to the 5th minus 7 over x to the 6th. So notice that all of the fractions where x is in the denominator, all of these are going to be 0 when I evaluate the limit, which leaves me with negative infinity to the 6 times 1, which would be negative infinity. If I decided to use the theorem, which we do have to be careful about using theorems because on an exam oftentimes you won't have the theorem to refer to. So if I did use the theorem, it would be a lot nicer because I'm just looking at the leading term. If I write this as negative limit, factor out the negative again, of x to the 6 minus x squared plus x minus 7, and I use the theorem, this is my x to the n. Yeah. Since this is an even exponent, this whole piece by the theorem is going to be positive infinity, which means by the theorem, the negative is still in the front. We have negative infinity. So we could compute it directly, or we could just use the theorem to evaluate the limit. The next theorem is going to be with rational functions. So recall from algebra, a rational function is just a fraction with a polynomial on the top and bottom. So what we want to do when we look at the end behaviors, how these rational functions behave at the ends, and look at other asymptotes of rational functions, is what we want to do is look at the degree of the polynomial on the top and on the bottom and compare them. So for property A, if the degree on the top is smaller than the degree on the bottom, then the limit as you go to positive or negative infinity is going to be 0. So y equal to 0 is going to be your horizontal asymptote. B says if they're the same, then when you take the limit as you go to negative and positive infinity, it's just going to equal to the fraction of these leading coefficients, a sub n and b sub n. And that's what your horizontal asymptote would be, that fraction. Property C says that if the degree on the top is larger, then the limit's going to be negative or positive infinity, and there is no horizontal asymptote. There is a special case where if the top is 1 more than the bottom, there's still no horizontal asymptote. However, there is a slant asymptote. So I'm going to use SA for slant asymptote. A slant asymptote is just a line, and we usually write it in the form y is equal to mx plus b. It just happens to be slanted. So if the graph is going to follow the slanted lines, it's going to go off to negative or positive infinity. The last property is with vertical asymptotes, so I'm going to use VA for vertical asymptote. And it says that here you have to be careful that your function is reduced. So the vertical asymptotes are going to be at the zeros of the Q, the denominator. So let's go ahead and look at this next example. We're supposed to evaluate the limit, state if there's a horizontal asymptote, and then if necessary divide by the largest power of x in the denominator. So if we were to just evaluate by plugging in infinity for x, notice that this would be infinity over infinity plus infinity minus 3. So infinity over infinity. Again, this is an indeterminate form. Indeterminate just means we cannot determine the limits. We have to do something else. Well, if I were using the theorem, I would see that this limit is going to be equal to 0. Because the degree on the top is smaller than the degree on the bottom. So if I were using the theorem, then the limit is equal to 0, and the horizontal asymptote is y equal to 0. So again, let's just say that we're not using the theorem. Say it's an exam and you don't have the theorem for reference. Well, we did get an indeterminate form, which means we have to do something more. So that something more is to create a fraction as we did before. And again, this is a strategy that we often use when we get the indeterminate form of infinity over infinity, or infinity minus infinity. We create fractions. So I'm going to divide all the terms top and bottom by x to the 4th. In the numerator, we're going to have 2 over x squared divided by 1 plus 2 over x to the 3rd minus 3 over x to the 4th. So you see how we created these fractions, and now when we evaluate the limit, as x goes to infinity, notice that in the numerator this is going to go to 0, And the two fractions in the denominator are also going to go to 0, which leaves us with 0 over 1. And that is not an indeterminate form. 0 over 1 is just 0. So we got the same solution as using the property, but this is using algebra instead of using the theorem. So now we're going to put all this together with another example. The example on the next page. We're going to use the theorem to find any asymptote, so horizontal, vertical, slant. And if there is a slant asymptote, we're going to use long division to find it. So that would be something that you might have seen in your algebra course. So by the theorem, I could see right away that since the degree on the top is larger than the degree on the bottom, there is no horizontal asymptote. But 3 is 1 more than 2. So there is going to be a slant asymptote. Really should have wrote essay, huh? Okay, so let's see if there's a vertical asymptote. Well, if I look at this function, the denominator factors into x minus 2x plus 1. So if I set the denominator equal to 0, I see that x is equal to 2 and x is equal to negative 1 would be the vertical asymptotes. So I found all the asymptotes. No horizontal, slant asymptote, 2 vertical asymptotes. But what is the slant asymptote? That we don't have. So how we find the slant asymptote is we do long division. So we take the divisor, which is x squared minus x minus 2. And we divide that into the quotient, or the function on the top, which would be x to the third. Notice I'm missing an x squared, so you could leave a space or a 0x squared placeholder, so that when you subtract down, you have your like terms lined up. Okay, so now the long division is that we would multiply the x squared minus x minus 2 by x to get x to the third minus x squared minus 2x. So whenever you do long division, you subtract down. After subtracting, I'm going to have x squared plus 4x and bring down the negative 1. So if I multiply my divisor by a positive 1, we have x squared minus x minus 2. And then again, remember long division, we subtract down. So 4 minus a negative x would give me a positive 5x. Negative 1 minus a negative 2 would be a plus 1. Now the slant asymptote is actually this quotient on the top, which would be y equal to x plus 1. And that's going to be the horizontal, or the slanted line that my graph will follow. So we're actually just ignoring this remainder and then just looking at the quotient on top. And there is a reason why. By doing this long division, we can write our function in a different way, as quotient x plus 1 plus remainder 5x plus 1 over divisor x squared minus x minus 2. Notice that this last piece is actually going to go, if I were to take the limit as x went to infinity, this goes to 0 because the degree on the top is smaller than the degree on the bottom, which is kind of why we ignore that remainder. It doesn't make a difference when you're looking at how your graph behaves. The only thing that matters is the quotient part, this here. Okay, well, let's move on to another example. And the reason why I'm bringing up this example is because there's a square root in there. So something to note is you can't really use the properties of rational functions and polynomials because this is neither a rational function or a polynomial. It has this square root in it, and we have to be very careful with square roots. If I were to put negative infinity in, this would be negative infinity over positive infinity plus positive infinity minus 4, and we're taking the square root, which would just be negative infinity over positive infinity. And again, that's indeterminate. We don't know what this means. So I need to do something more. I'm going to use that strategy of creating fractions. But what I'm going to do is I'm going to look at the square root. And underneath the square root, what I'm going to do is I'm going to factor out the largest power of the x, which is the x squared. So I'm going to ignore the numerator, and I'm going to look at underneath the square root, factoring out the x squared. What remains would be 1 minus 3 over x minus 4 over x squared. So this is sort of a special case that I wanted to cover. In the denominator, if I were to break that square root up, I would have 6x over the square root of x squared, which is not x, by the way, times the square root of 1 minus 3 over x minus 4 over x squared. Okay, so I created these fractions. This square root of x squared, we have to be really careful about that, because square roots are always positive or 0. They're never negative. So this whole thing has to be greater than or equal to 0. And something that we want to make sure that we understand is that I can't just write that as x because of this. The x values are approaching negative infinity. They're negative. So if I were to just cancel this and write x, x is a negative number. That means my square root would be negative, which cannot happen. So this is actually the limit as x goes to negative infinity of 6x over absolute value of x. So that'll ensure that my simplification does not give me a negative x. Okay, it would be really nice if I could cancel the x from the top and bottom, but I really can't. Not until I get rid of the absolute values. So we're going to review property of absolute values. To get rid of the absolute values, if what's inside the absolute value is greater than or equal to 0, then we drop them. If what's inside the absolute value is negative, to make a negative number positive, you take its negative. So we take negative a. In our case, since our x values are approaching negative infinity, they're negative. So to get rid of the absolute value, I need a negative in front of the x. So I write 6x over negative x, right? Because my x values are negative, that'll ensure that it's positive. And now I'm where I want to be. I can now cancel the x on the top and bottom, And again, I'm bringing up this example because it covers a lot of algebra techniques that you might have forgotten. So we can cancel the x, remembering that there's a negative in front of that square root. We have the limit as x goes to negative infinity of 6 over negative square root of 1 minus 3 over x minus 4 over x squared. Okay, now I think I'm ready to evaluate this. These fractions, remember these are going to go to 0. So this limit is actually going to be equal to 6 over negative square root of 1, which is just equal to negative 6. All right. So that's the limit. And since it is a real number, that means that y equal to negative 6 is going to be the horizontal asymptote. So that's it for section 2.5.